Okay, so let's get started. So today I'm going to talk a little bit about the message passing interface, otherwise known as MPI, which is the predominant parallel API used in scientific computing these days. And this is a fairly long topic, so stick with me here. I'm only going to touch on the core features of MPI, and we'll leave the more advanced and esoteric features to a future date if people are interested. So first, a little motivation. Why are we trying to parallel process in the first place? Well, usually that's for the purpose of performance, right? Either we want to solve a bigger problem than we're capable of solving on our individual desktop or workstation or whatever development platform we happen to be using, or we want to reach a solution faster, or potentially both of those things. There's little argument these days that the hardware is becoming intrinsically more parallel, right? You go out and buy a laptop or even a cell phone nowadays, and you're going to get many cores, physical cores, in the CPUs that are on those platforms. And when we're buying servers for high performance computing or scientific computing that we do at CCR, we're typically buying upwards of 40 cores per node these days. And a little bit of justification, parallel programming is not easy, right? I mean, I'm not going to convince anybody that even sequential programming is easy, and parallel programming just adds an extra layer on top of that that you have to deal with. So don't let anybody tell you that it's actually easy to do, because it is not easy to do. So forgive my cartoon, but that's pretty much all I'm capable of drawing. So the big picture is that we're going to take a problem that we're trying to solve, that could be from any discipline, and we're going to decompose it into processing elements or CPUs. Now, of course, it's trendy nowadays to talk about alternatives to CPUs like GPUs or other forms of accelerators, but we're going to defer that to a future topic as well. And we're just going to focus on CPU cores for the purpose of MPI today. So we're going to decompose this problem into CPUs. And if we're really lucky, we have a nice uniform picture here where we can just take it and subdivide it nice and neatly, either in 3D or 2D or 1D, into nice little blocks that we can farm out to the individual processing elements, and everybody has an equal amount of work to do, and everybody's happy, and things go according to plan. Of course, reality then intervenes, and we have a more complicated problem that we have to solve. So the particular problem that I'm showing you here is a geospatial terrain map. It's being broken up into a 16-way parallel calculation with MPI. Each one of the MPI processes, their particular region is colored differently in the picture here. So you can see that the smallest one, which is the dark blue one, which is slightly off center, in the middle there, that one is much smaller than the rest. And the idea here is that you're trying to create an equal load balance among all the parallel processing elements. And there's something interesting happening in that small patch there, which is why it has a physically smaller region to deal with. And this, of course, is also a time evolution problem that's being solved. So as you can imagine, as things evolve in time steps, you're actually going to have to dynamically adjust the load balance amongst all the processing elements. So it becomes a more complicated problem, of course, as you would expect. But if you were in the simple case where you had a nice, easily decomposed, say, a Monte Carlo-ish problem where everybody has a nice equal amount of work to do, then you're lucky. The reality is usually quite a bit different from that. Okay, so there are a lot of parallel programming models out there, but in scientific computing right now, it usually comes down to two. The message passing interface, or MPI, and OpenMP, which is the open spec for multiprocessing, which is a thread-based model. I'm actually going to talk a little bit more about OpenMP in a couple of weeks, so we'll defer OpenMP for the moment. We're just going to talk about MPI. And of course, it's fairly popular nowadays to actually combine both of these methods into one. And I'm actually going to show you an example at the end of the talk today about how you actually in practice can do that. And we'll revisit that again, the OpenMP talk in a few weeks. So just again, to illustrate how important MPI is these days, I pulled this from the NERSC workload study from 2014. If you're not familiar with NERSC, it's the National Energy Research Scientific Computing Center. It's the Department of Energy's, probably their flagship computing center for the Office of Science, so for non-classified work. Roughly speaking, they have about 12,000 nodes at the time this report was compiled that served all of DOE. And as, of course, you can tell from the plot there, MPI is used pretty much universally across all of their applications. And OpenMP is used a little less often, and then you drop down into even less popular parallel APIs that are basically just research topics at this point, other than POSIX threads, which gets to use more on the operating system side. So what does a message passing model look like? Well, again, my cartoonish picture here at the top, you have a processing model in which each copy of the executable, and that's the squares at the left there, which I not so inspirationally named a.out as the name of the executable, has its own copy of the data. Those are going to be completely separate processes in the Unix sense with their own process IDs. And the only way they actually share things is by sending messages back and forth. And those are the blue arrows for the sends and the receives, or you might have a collective communication that involves more than two processes at a time, a broadcast or a reduction or something like that. And of course, this goes on over the course of time. And it's, the communication pattern is entirely dependent on the type of problem that you're actually trying to solve. So this is a very general purpose model, which is one of the advantages that this model has, is that you can run it anywhere. Right? You can run it on a bunch of laptops that are hooked together. You can run it in a high performance cluster like CCR has. You can run it on a supercomputer. You can run it anywhere. It also gives you a great deal of control over how your program is actually put together and how you actually construct it. And it gives you the ability to achieve the maximum level of performance. The disadvantage, of course, is also closely related to the advantages. Since it gives you that much flexibility, pretty much everything is left to the programmer to actually implement these things, right? And one thing that I want to emphasize a couple of times today is that MPI is engineered for performance. It's not engineered for reliability or ease of use. It's engineered for performance. So another gotcha that I like to mention at this point is that the MPI spec itself does not cover the mechanism for how the actual application gets launched in the first place, which in the MPI lingo is usually referred to as the task launcher. It's entirely implementation dependent. And for people who are new to MPI, that is usually a chronic pain point that takes some getting used to. Okay. A little bit more background. What are we going to talk about today? Well, we're going to talk about MPI in the core sense. This is going to require at least some passing familiarity with C and Fortran or Fortran. Although you can use MPI from other languages, it's fairly popular to use it from Python or R these days, and also Java. They just leverage the C bindings in their interfaces. And I'm not going to have time to cover in the 30 minutes that I have available today anything more than just the basic core features. But I'll touch upon the others so that you know that they exist. And if there's sufficient interest, we can always come back and revisit those at another time. Another thing I'm not going to have time to talk about today are more algorithmic things, right? More general algorithmic approaches to parallel programming. I'm not going to talk about scaling or Amdahl's law. There are CSE classes you can take if you want to drill deeper into those, or we could potentially come back and revisit those in a separate talk in the future as well. And I'm not going to get to the more advanced MPI features, one-sided communications or MPI-IO or topics like that. So the MPI spec itself, well, the first version came out in '94, so 26 years ago today. It's been around for a long time, but most of the core features were pretty well laid out in MPI 1. MPI 2 and MPI 3 came out later and enhanced and clarified some things, added some relatively minor new features, some more minor than others. What was built into MPI 1 from the beginning, of course, were all the point-to-point communications, the sends, the receives, the collective operations, the reductions, the broadcasts, the scatters, the gathers. It also gave you a great deal of flexibility in terms of how you actually put these processes together into groups and domains and topologies. And one of the nice features about even from the outset is it built in an extensive profiling interface that you can tap into to see what's actually going on inside your MPI calculation, which can be very important. MPI 2 came out later, about 10 years later. It added some dynamic process management that almost no one uses to this day, but it still exists. It did add the very useful input and output features, so you can do true parallel I/O, supposing that you have a hardware platform that supports that. Large scale calculations do make extensive use of MPI I/O these days. It added one-sided operations, so those are gets and puts and accumulates instead of the sends and receives. And it added C++ bindings. MPI 3 then came out a few years after that and promptly took the C++ bindings away, mostly because nobody was actually using them. If for C++ programmers, you can just use the C bindings, which is what almost everybody ended up doing because the C++ bindings didn't add a whole lot of functionality, or actually almost no functionality on top of that, so that they deprecated those and everybody just uses the C bindings these days to make it a little easier to maintain. And then they added a few other additions to MPI 3. If you like books, I usually recommend these 3. The first one is a good intro. The second 2 are excellent references, the MPI complete references from MIT Press. If you're not interested in paying for the books, there's actually a free copy of the first edition of the MPI complete reference at NetLib there, if you want to take a look at that. And if you're just interested in the syntax for the MPI routines, there's a handy website that I give you here that you can use to check those. Okay, so let's get right into it. How do we actually do this? Okay, so as you can anticipate from what I've said so far, MPI is a very big spec. I didn't bother to count the number of functions that were added in MPI 3, but we're well over 400 functions. I promise I'm not going to discuss a large number of those today. I'm only going to hit upon a couple. The vast majority of programs can use a fairly smaller amount of these functions. The real advantage that you get from having that amount of flexibility are people who are writing libraries and things like that. So usually MPI is the right size for the type of problem that you're trying to solve. And you can tap into the additional functionality after you learn the basics to leverage what you need from the actual spec. There are, of course, a large number of available MPI implementations. So the 3 most popular open source ones are the ones that I have here, listed here. MPitch is the original sort of reference spec implementation for MPI. It originally came out of Argonne National Laboratory, and in fact, it's still maintained by Argonne. MVA Pitch is from DK Panda's group at Ohio State University. It basically takes MPitch and adds functionality for a lot of specialized networks and adapters, like InfiniBand. OpenMPI is basically all of the other open source projects that existed like over the last couple of decades that sort of grouped together and contributed towards another open source implementation of MPI. So if you're using the package manager on your Linux workstation or your Mac laptop or whatever available to you, you can easily grab one of these open source implementations and install it. For the purpose of running at CCR, we usually recommend that people use Intel MPI, which is one of the commercial MPI implementations. Intel just basically took MPitch, or MVA Pitch rather, and customized it for their own use. And I'm gonna go through the advantages of using Intel MPI in our environment. But you know, the implementation that you use is entirely up to you. So what does a basic MPI program look like? Well, it looks like this. Up at the top, you have to include your MPI header files that basically determine how you interface with the spec itself. Then you declare your variables and your data structures just like you normally would. You have to initialize MPI. I'll go through the function call for that here in a second. In your main program, you'll have to instrument it for message passing, depending on what type of application that you're trying to write, and then you shut MPI down at the end. That header file, you can probably guess what the name of that is going to be. In C and C++, it's MPI.h. In Fortran, there should be a module for it. It's just use MPI. The naming conventions for MPI are typically capital MPI underscore. And then if you're in C, the first letter of the function call is capitalized after that. Fortran, of course, is case insensitive, so it doesn't actually matter whether you capitalize it or not. And then in the case of MPI constants and other data structures, the convention is to capitalize all of it. Okay, so initializing. Again, you won't be terribly surprised to learn that the first MPI call has to be called MPI init. For C and C++, you pass it the arguments that you use in your application. And then the last MPI call has to be MPI finalize. And notice, of course, there's a return code for each of these. Now, it doesn't have to be the actual first function call in your code, right? You can have as much code before the MPI init that you want. Of course, all of that code will be serial, which is usually not a good thing in a parallel application. So usually the MPI init is quite close to the beginning of the program, but it's only required that MPI init be the first MPI call that you make. So those return values, you can actually compare those with a predefined MPI handle, MPI underscore success, to test whether or not your call was successful. MPI communicators are basically just another bit of lingo here for the groups of processes that can actually communicate with each other. And it won't surprise you too much to learn that any given MPI process can be a member of multiple communicators. So within each communicator, another bit of lingo here, the rank of a process is the number starting from 0 to n-1 that uniquely identifies it within that communicator. So this rank then gets used when you're actually constructing all your messages to send back and forth. So one predefined communicator that you always have is MPI_com_world is the predefined communicator that consists of all the processes that you started when you started your application. And then you have extensive calls that you can use to manipulate that, split that, lay on a topology or other type of data structure, and do whatever you want to from there. So usually right after the MPI init are two more calls that you might anticipate, MPI com rank and MPI com size. Com rank just says, okay, what is my rank within this communicator? Com size just says, how big is this communicator? So after your MPI init, typically every single application will then issue these two calls with MPI com world as the communicator and determine what their rank is and what the overall size is for the application being run. So MPI has this extensive set of data structures. Let's take a few minutes here to talk about those because those are going to be kind of important going forward. They usually, again, another bit of MPI lingo here, they refer to these as handles, right? They usually get returned by the MPI routines and used as arguments. MPI success, we already saw, right? You can use that to test MPI error codes. And they don't have to be identically implemented within each particular MPI implementation. They're even different within C and Fortran. And of course, MPI com world is our default communicator. So MPI also has this notion where they have their own data types, right? And you will legitimately ask, well, why did they bother doing that? Well, think back to more than 20 years ago when the computing environment was much more heterogeneous than it is today, right? Today, everything is basically, well, not everything, but most things are Intel architecture that we're using for scientific computing. That was not the case in the 90s, right? IBM still had a very popular set of processors that they maintained called Power. HP had their own PA RISC processors. You know, the list goes on. Sun had Spark processors. It goes on from there, right? And each one of these had a different numerical representation that was used behind the scenes. So MPI has its own data types to allow for these things to be automatically translated between the different computing platforms. So you could run a single MPI application across multiple different architectures. Nowadays, it could be, you know, say you have some Intel chips, you have some ARM processors that you're going to throw into the mix or some other type of accelerator. You can actually do this, and MPI will translate the data types between their intrinsic numerical representation on each one of these platforms. And you as the programmer don't necessarily have to worry about the details of how that is done. And of course, you can build your own data types from the basic MPI building blocks. So the convention ends up being that you declare your program variables just like you normally would within C or Fortran. And then when you actually call the MPI routines, you use the equivalent MPI type names, and that will handle the translation that would necessary between them. So again, in C, you can anticipate what these are going to be: MPI_float for floats, MPI_double for doubles, so on and so forth, and the equivalent on the Fortran side. Okay. So we've already done enough to do a simple hello world program in MPI. So that's shown in the box here. You can see that line 2 there, we're including our MPI header file. Line 7, we do our MPI init. 8 and 9, MPI com size and com rank. And then we print out hello world, I am process I of n, and then we shut it down. So we're not doing anything terribly interesting in this example other than printing hello world, but that's enough to illustrate how to actually run this thing. Okay, so back to what it looks like when you actually run this. So in CCR, we usually recommend that you use Intel MPI, as I mentioned before. One of the reasons for that is it has very nice support for multiple networks. It could be InfiniBand or OmniPath, or the various different flavors of InfiniBand, or it could be plain old TCP/IP. It also has handy integration with the other Intel software tools like the math kernel library. And it has some very nice CPU pinning and process affinity options that I'm going to cover in a little bit more detail, especially towards the end here, and then again when I talk about OpenMP in a couple of weeks. So what does it look like when we actually try and run our hello world program here? Well, first we have to load the necessary modules. So we do a module load on the first line here, module load Intel MPI. We get a little bit of feedback from the module system if we want to actually source the files necessary to do some more advanced features, but we don't actually need to do that for this example. Then we're going to compile our hello world C example here, which is hello2.c. Notice that I'm using a compiler wrapper to do this. Again, this is something that is not specified by the spec. It is entirely implementation dependent, but the vast majority of MPI implementations, and I believe that's true for all of the open source ones and almost every commercial one that I can think of these days, that there is a compiler wrapper that will help you get all of these header files and libraries set correctly. So with Intel MPI, you can actually pass the -show flag to the compiler wrapper and it will show you exactly what it's doing behind the scenes. And you can see here this very long list of include file locations and library file locations that you would be very hard pressed to guess without having a handy compiler wrapper to take care of it for you. So we compile it with a compiler wrapper. And then to run it, well, the MPI spec suggests that the name of the task launcher should be called MPI exec. So that is what you can use most of the time. And we're doing this just on the CCR front end here. So we'll do an MPI exec. We'll tell it to run 4 processes. That's the -np4. And we can see hello world, I am process 0, 1, 2, 3, or 4. Great. Now, I should warn you that, of course, that's not necessarily what the task launcher is going to be called, depending on what MPI implementation you're using. And in fact, even at CCR, when you're in SLURM, you're going to want to use srun as your task launcher instead of MPI exec, as I'll show you in a later example. So another nice feature of Intel MPI is it has a very nice processor affinity interface. If I turn the debugging level up to 5 here, I do that by I_MPI_debug, this environmental variable, and then I rerun the same executable, it will spit out a whole bunch of useful information about where it's actually putting all the processes. So you can see it's using shared memory, SHM, for the data transfer mode. We're just running it on one machine, so that makes sense. You can see the first column here, it's indicating each one of these things per MPI rank. It tells me that all 4 of these ran on the same front end node. That's not unsurprising. And you can actually see that it's telling me what CPU cores are eligible to run each one of these processes. You can see it's actually split it up across the different sockets and then 2 subdivisions of each socket on the front end. This is nice, useful information later on, especially when you're running in SLURM, to make sure that your code is actually running on the nodes that you think it should be running on, that it's not oversubscribing the cores, and that it's using the right network to actually share the messages back and forth. Okay, so that's hello world. Now let's talk about how to do something a little bit more involved. Let's talk about the point-to-point communications that MPI offers. So in MPI 1, it only explicitly allowed 2-sided communications, right? Sends and receives. Later on in MPI 2 and MPI 3, you can use gets and puts for so-called one-sided operations. And that's a much more sophisticated way of going about this, and a way to get a little bit less overhead in the messages, but the concept remains the same. And I'm only going to have time to talk about the 2-sided stuff today. We could revisit the one-sided stuff later if there's enough interest. So these point-to-point communications are explicitly 2-sided, right? It requires the active participation of both processes. A message usually has an envelope, which contains the destination information, and a body or a buffer that's going to be sent back and forth. And once you actually talk about these point-to-point communications, the sends and receives, you could build all of the rest of the MPI functions from them, right? They're the fundamental concept here. So these 3 points to describe a message body. Well, there's a buffer, right? The starting location in memory where the data is going to be found. So in C, that's the actual address of an array element, right? You're going to give it a pointer. In Fortran, it's the name of the array element, which is functionally equivalent in Fortran to a pointer. The data type, right? The type of data that you're going to send, usually one of the predefined types, could also be user-defined type. And the count, the number of items being sent. And that's all you need to tell it. So there is a significant gotcha in this, and if this were an interactive class, I would pause here to ask the question of what is the gotcha? But as this is non-interactive and I'm just speaking here, I'll tell you, the gotcha here is that all of this has to be contiguous in memory in that buffer, right? You're sending it a starting location in memory, the data type, and the count. All MPI is going to do is it's going to look at that starting location in memory, copy that many bytes out for the buffer, and send them along. it will do absolutely zero error checking on this for you, right? That is entirely left up to the programmer. So the thing that usually bites most students the first time they encounter this is they take a 2D array in C, try and pass this in when it's not contiguous in memory, and then they get garbage out at the other end. There's no error, right? They just get junk out on the receiving end of the message, and that's why. Again, remember, it's engineered for performance, not necessarily for ease of use. So in terms of the message wrappers themselves, you have to give it the communicator, the source, the destination, and then there's an optional tag that you can use to label classes of messages. You also have the determination of whether or not to do blocking calls or non-blocking calls. And these are basically just whether or not it's a synchronous call or an asynchronous call. So for a blocking send, it's now safe to overwrite that sent message buffer. For a blocking receive, I've got the data and it's ready to use. The non-blocking equivalents that I'll show you, the routine returns immediately, and then it's up to you to test whether or not the message has actually been sent. So of course, the advantage here is that the asynchronous communication gives you the advantage of layering some additional computation in there while you wait for the messages to go back and forth and get better performance that way. So syntactically, MPI send and MPI receive look like this. Again, here's our buffer, our count, our data type, our destination, our tag, and then our communicator. And you'll note that the MPI receive picks up one extra argument here. That's the status handle that you can actually use to test whether or not the message has been received successfully. And you can test that by looking at the source, the tag, and any potential error that actually came back from this. So let's do a simple cooked up example here. So the first part of this program looks just like our regular hello world, right? MPI init, com rank, com size. I'm even going to printf the same hello world message I had before. And then we're just going to send a simple test message between two ranks here. So the destination is going to be the n-1 process, and the source is going to be the rank 0 process. So if I am the source, I'm going to construct a buffer here and then send that buffer off to the destination, which is on this side. Then on the destination, you're just going to actually test the status of whether or not that's been received. Easy. Well, it's easy when you've got two processes. So for the receive, completion's easy, right? I have the data and I can now use it. Sends are a little trickier, right? It completes when the data has been stored away such that you can reuse the send buffer. It's usually non-local. So in MPI implementations these days, even the so-called blocking send is somewhat asynchronous, because what will happen is it will get copied off to a local buffer and then it will return. It doesn't mean the message has actually been sent yet, right? It's still in the process of actually sending it. So the advantage of all this buffering going on is it decouples the send-receive operations, even for the blocking sends. The disadvantage is there's a little bit of additional memory-to-memory copying going on here. And another disadvantage is the amount of buffering is entirely implementation dependent. Well, not necessarily entirely, right? As the programmer, you can actually go in and exert complete control over this, should you choose to do so. Most people don't, right? They leave it up to the default. So if you're not careful with this, it's actually fairly easy to cause a deadlock situation in MPI codes where the programmer basically assumes that the message is being copied off to a local buffer, but once the message buffer grows to a certain size, and it's implementation dependent how big that size is, it will then lock up waiting for the message to actually be sent. So, any system will eventually run out of buffer space. So this comes up fairly often as an early problem that most people trip over too. Again, when you have two processes, it's pretty trivial to see when this is going to happen. When you have n processes and a more complicated communication pattern, it's not always so easy to see when this is going to happen. But if your code locks up, usually the chances are that you've got a deadlock situation going on here. So the easy way to get around deadlocks, of course, is to use the non-blocking or asynchronous forms of MPI send, right? And that's MPI I send and MPI I receive. To this day, I still have no idea why they chose I as the letter to designate asynchronicity here, but that's what we've got. The syntax is exactly the same, except now, of course, we've got the request handle available in the non-blocking send as well. And the reason that's available, of course, is so you can actually test it to see whether or not the message has actually been sent. Right now, again, it's entirely up to you as the programmer to make sure you do not overwrite the send buffer until that send is complete, right? Otherwise, you will corrupt your own messages. The routines for doing this is basically you have two options. There's MPI_wait, right? Which given a request handle, it will do what it says. It basically will wait until that is done before it returns. Or the more performant option is MPI_test, which you give it a request handle, and then you can actually get back a status, whether or not it is now safe or unsafe to proceed. So what's the advantage of this? Well, the advantage of this is it gives you the ability to actually overlap some computation with the time that it's actually spent sending the messages back and forth. So let's look at a more practical example for this, right? So I pulled this from the source code for the popular HPCG benchmark. This is high performance conjugate gradient. It basically tests a very large sparse matrix solve using MPI. So I pulled this snippet right from the source code for this. So you can see that what they're doing here in this very first loop is actually doing a non-blocking receive. So they post the receives, and then while they're actually waiting for this to go through, they construct their message buffers for the sends, and then do some testing down here at the end to make sure that everything is done before they proceed. And this being a raw chunk of source code pulled directly from GitHub, you can see there's still some interesting comments in here saying that, hey, we should come back and thread this at some point to get even more performance, which they obviously have not yet done. Okay, so running low on time now. So MPI collectives. So the point-to-point communication routines that I just talked about can be used to build any number of more complicated algorithmic functions that MPI has already done for you, right? So if you need to do a broadcast, there's an MPI routine for that. In fact, if you want to do an asynchronous broadcast, there's an MPI routine for that now too. If you want to do gathers or scatters, you can do those. If you want to do a vectorized form of gather and scatter, you can do those too. If you want to do reductions or all reduce is basically a reduction plus a broadcast. There's already an MPI function for that, right? So I'm not going to go through these in gory detail because there's no possible way to do that in 30 minutes. But there are lots and lots of MPI functions. So any particular type of functionality that you want to do, chances are really good that there's already an MPI function for that. Other things that we don't have time to talk about today, user-defined data types, right? You can construct your own user-defined data types as opposed to relying on just the fundamental data types for sending messages back and forth. And there's an extensive set of routines that MPI has for doing that. Constructing different communicators and groups, that's particularly useful if you're writing a library, right? The libraries usually want to decouple what they're doing behind the scenes from what the application end user is doing in the front side. So they usually set up their own sets of MPI communicators for doing so. You can also construct process topologies. You do MPI-IO and the dynamic process, all these things, right? So if there's sufficient interest, we can come back and talk more about those in a future talk. So one thing I do want to mention, considering I'm going to talk in a couple of weeks about OpenMP, is that it's quite popular, as I indicated earlier from that NERSC workload report, to couple together MPI with something else. And these days, the something else is usually OpenMP. So you use MPI for doing message passing between individual machines, and then within a machine, you use OpenMP to take advantage of shared memory. So even though I'm not going to talk in detail about OpenMP today, I can show you an example of what it looks like to run that. So you can take advantage of the lower overhead potentially that OpenMP has for using the shared memory and cores within a particular node while sending messages back and forth between the nodes. One of the downsides of trying to do this is you have to be very careful about how the MPI processes and OpenMP threads get placed, which is another reason why we usually recommend Intel MPI at CCRs, because it has a very good interface for doing so and also a good interface for reporting back what is actually being done. And you can have dramatically different performance results depending on how this gets done. Right? The worst case scenario you can imagine is that you have a whole lot of threads all running on the same physical CPU core. It's actually quite easy to end up in a situation where that happens, and of course that will shoot your performance right in the foot. And then how does this interact with the resource manager, right? For example, SLURM. That's also important. So let's go back to that HPCG benchmark, right? It uses the Intel math kernel library, MPI and OpenMP. In fact, Intel gives you a nice little pre-compiled executable you can use to run this. So you can see this down on line 29 of my sample SLURM script here. I'm just going to use the one that comes with Intel MKL. you should be able to copy the script and run it yourself if you want to play around with these things. So I'm going to run this on the Skylake nodes at CCR. I'm just going to grab 2. The recommended way of running this on modern machines is to put 1 MPI task per socket and then use the remaining cores per socket with OpenMP. So for CCR Skylake nodes, you see this up at the top for lines 2 through 4. I'm going to request 2 nodes, 2 tasks per node, 16 CPUs per task, because these are 32 core nodes, 16 cores per socket. And then the rest of the usual stuff for running a SLURM script. I'm going to turn this MPI debug level up to make sure I get useful information about what is running where. I'm going to set the number of OpenMP threads, which I haven't talked about, but will in a couple of weeks, to the SLURM CPUs per task that I asked for up here, which will be 16. I'm going to echo that out to make sure it's doing what I want. And then this other piece, remember I said that srun is the parallel task launcher we want to use for MPI and SLURM. So that's the srun command down there. I do have to use this extra setting up here just above that, which is to tell Intel MPI to use SLURM's version of the process matching interface as opposed to Intel MPI's, which tends to mess up. So you never want to leave this line out. You'll find that in all of CCR's sample MPI scripts. So assuming that I do all of this correctly, it should run the way I want. I can actually check that once it's actually running. So what I'm showing you here is I'm doing SSH into the node that it's running on and running htop. I want to see all those cores busy, which you can see from the graphic up at the top, they are. I can see in the process list there, I've got my 2 processes per node. I can see the CPU percent is about 100% per CPU for all 16. And it's matching pretty closely to what I expect. It's also using about the same amount of memory that I expect. So good, it's actually appears to be doing what I want it to. You'll also note that I kind of glossed over one other setting here, which is another OpenMP specific thing that I'll talk about in a couple of weeks. This is Intel specific. It's the KMP_affinity variable. I turned it to verbose, and then these other settings basically tell it to use adjoining cores on each socket and to ignore hyperthreading. And then in the text output that we see from setting the I_MPI_debug variable, we'll see that I've got 2 tasks running on each node, exactly what I asked for, and then it will spit out what OS core setting it's actually respecting on each one of those. And again, it's basically putting 16 threads on each socket, which is exactly what I want. So good, it worked the way I wanted it to work. And again, I'll talk more about the OpenMP specific parts a little bit later, but I just wanted to show you one more example of a more sophisticated MPI run. Okay. So I'm actually over by a couple of minutes, which doesn't surprise me. If you're interested in more details, there's a bunch of additional MPI, more extensive MPI talks in our training set. These are hanging off the Fresh Desk page that I've got linked here. If you're interested in a slightly different perspective, you can look at the Exceed user training page, which I've got listed here. That has a whole bunch of extra materials on it, not just MPI, but they've got some excellent MPI tutorials up there as well, including some self-guided ones if you're interested in taking those. And then last but not least, the upcoming talks in the CCR Virtual Workshop series. We're running out at least until mid-July or so. So that's it for the intro to MPI. It was meant to be the 30-minute version. I apologize. It was more like the 35-minute version. I knew I was going to go over. Hopefully I didn't go too fast. I'm happy to take questions that anybody might have.